Okay, today we are going to talk about the kinetic molecular theory. A theory is an explanation of a pattern. Molecular is going to refer to the particles, either atoms or molecules, and kinetic is motion. So we are going to look at an explanation as to why molecules move in a certain way. And we're going to primarily focus on gases for this morning. Now, the kinetic molecular theory is going to be based on the idea that particles are constantly moving. Okay, so they're always moving in some way, shape, or form. And this can be applied to a solid, a liquid, or a gas. And I think most people are pretty good on the fact that particles move in a gas or a liquid. And the reality is that they still are moving in a solid as well. It's just that they're in a fixed position and they just have a small amount of vibration. So when we talk about solid, it's just a small amount of vibration for those particles. And it's all based on the energy of the particles as well as the forces that act between them. We're going to spend a lot more time on this idea of the forces or intermolecular forces a little bit later in the year. And right now we're primarily focusing on the energy. And again, when we're talking about particles, we kind of group together atoms or molecules. Okay. And really, I guess we could say compounds too, but that's the reality of what we're talking about movement-wise when we talk about particular motion. Now, with the KMT continued, the KMT of gases. Okay, so like I said, gases is really what we're going to focus on, and it's a model of an ideal gas. And I think it's important to point this out because scientific models are not perfect. They're not 100% accurate all the time, but they do provide us a way to study something that may be more difficult to study otherwise. And we're going to talk about this as being an ideal gas. We kind of take some liberty, so to speak, and look at things from a perfect perspective. It would be a hypothetical gas that perfectly fits all of what are called the assumptions or the main ideas of the kinetic molecular theory, knowing full well that this isn't always the case, but it still gives us a focal or a basic baseline. And there's 5 basic main ideas. Just like Dalton's atomic theory, there's about 5 basic assumptions or ideas that are important. The first one is that gases consist of very tiny particles. Again, that whole atoms or molecules stuff, and that they are very, very far apart from each other. Okay, down here you have the classic case of or picture where you have the solid particles that are very close together and are in a fixed position. The liquids look a little bit more haphazard, more spread out, and then you have the gases that are extremely far apart from each other. The particles are compared to solids and liquids. And this picture doesn't even totally do it justice because it's a little bit more than that. But most volume is empty space and it's very low density. And if we remember, density is mass over volume. So in a given amount of space, there is much less mass for gases than solids or liquids, only because you have less particles there. And what this allows for is gases to be very easily compressed. Okay, we use stored gas a lot of different ways in our society, whether that be through aerosol cans or oxygen tanks or different ways. But it allows us to take a lot of gas, put it into a small amount of space so that we can have it when we need it, because we just take up that space. Okay, now here's a new concept here, is that all collisions between particles and container walls. Okay, so if we look down here, this is either going to be when particles run into each other, okay, or when a particle runs into the wall of whatever it's in. And we're going to say that all of these collisions are what are called elastic. And what we mean by elastic is the fact that there's no net loss of energy. Okay, what does that mean? Well, the easiest way I know how to explain this is that if you go to a bouncy house, one of those, maybe you haven't been there in a while, but a bouncy house where you run and jump and can bounce into the wall and you bounce right off. Well, when you run into the wall of that bouncy house and you bounce right back, that's an elastic collision. Okay, you're pretty much bouncing off with the same amount of energy that you bounced in with. Okay, as opposed to if we ran into a brick wall, what would happen then is that if we ran full force into a brick wall, all of our kinetic energy would be transferred to the brick wall and we would lose it. But the total kinetic energy of the system will stay constant. Energy can be transferred between particles, and again, if you think about, bumper cars type situation where something bumps into something and you transfer some of your energy into the next substance, but kind of along the same ideas of law of conservation of mass, is that the kinetic energy will stay constant, but it can be transferred between different particles. Okay, the next one is that particles are in continuous, rapid, random motion. Okay, and for the rapid random motion piece, this is going to be our gases. And since they're moving, okay, remember we defined kinetic energy earlier as the energy of a moving particle. So since they're moving and they have this rapid random motion, they have a lot of kinetic energy. And essentially that kinetic energy, here comes this balance again, is going to be able to overcome the attractive forces of the substances, of the particles. There's always some attractive force that's trying to pull these two things together. And in solids, obviously, it's stronger because they are stuck together. But in gases, they're moving so fast that they're able to stay away from each other. They're not able to be kind of sucked in or pulled closer to each other. Now, this kind of dovetails on that one as well, but number 4 states that there are no forces of attraction or repulsion. And what we're doing, the reality is that there are forces of attraction and repulsion between just about all types of matter, but we're going to assume no forces to make the science a little bit easier. And one of the best ways, I know how to explain this one, is very similar to billiard balls, or if you're playing pool. If you're playing pool, as soon as you hit, here comes the cue ball that you're going to hit something with, okay, they're going to scatter. They're going to scatter in all different directions. Okay, they bounce apart immediately so that they're not really attracted to each other or repulsed. They kind of act independent of each other, so to speak. Okay, then the last one, number 5, is that the average kinetic energy depends on temperature. Again, we've talked about this as well before. And if we give kinetic energy a mathematical definition, it's going to be kinetic energy is equal to 1/2 the mass times the velocity of a particle. Velocity is a fancy word for speed, just in a certain direction. But it's the mass times 1/2 the mass times the velocity squared. And essentially, if we think about relationships, velocity, temperature, and kinetic energy are all directly proportional or directly related. So that means as one goes up, the other goes up. And if we plotted any two of them on a axis, we would have a line with a positive slope that starts at the origin. And so the other thing is that if they're directly related, if kinetic energy goes up, the temperature is going to go up, and the velocity, or how fast they're moving, is going to go up. Okay, so they're all directly related to each other. And the same thing would be vice versa. If you take something and you decrease its temperature, well, then the kinetic energy of those particles would come down, and the velocity of those particles would come down. So they are all directly related and tied to one another. And one other statement, and I probably should change the terminology here, but at the same temperature, lighter particles, or I should say ones that have less mass, have higher speeds than ones that have more mass. And that is just a mathematical relationship up here. If I have something that has a higher mass, it's going to slow it down, and it's not going to be able to travel as fast. Okay? Alright, now the last thing we're going to talk about in this section is that this kinetic molecular theory accounts for several physical properties of gases. And some we've already talked about, but remember, physical property will not change the identity of something. Okay, so it will stay the exact same material. So if it's water, it's going to stay water. If it's carbon dioxide, it's going to stay carbon dioxide. We're not chemically changing it into something else. Okay, the first one is expansion. And expansion occurs because gases do not have a definite shape or volume, and they will always take the shape of their container. Okay, and this is something that we've learned for probably a long time. And this is due to assumptions 3 and assumptions 4. So the fact that they're moving very quickly, which is number 3, and the fact that they do not have forces of attraction or repulsion allows them to take the shape of their container. And fluidity is another property of gases, and that the particles can easily slide past one another. Actually, both gases and liquids are known as fluids. That's what allows them to take the shapes of their container, is because the particles, we go back to the assumption number 4 said no forces of attraction or repulsion. The particles have so little attraction to one another that they can easily slide past each other, and as the case with gases, will separate and get as far away from each other as they can in order to expand. Okay, a couple more properties. We've got low density, which we already talked about earlier. And remember I said that picture kind of did not do it justice, but if density is the mass per unit volume, okay, a density of gas is usually 1/1000th the density of the same substance in liquid or solid state. So if I had a solid, a liquid, and a gas in the same container, I would have about 1/1000th the amount of the gas particles than I would compare to the solids or the liquids. And then we have compressibility, which we've already talked about, and that gas particles may be crowded very, very close together since they are initially so far apart. Okay, and so what we have for compressibility, this is mostly due to assumption number 1, because it stated that they were so far apart. And same thing for low density. This also is mostly due to number 1, because they're so far apart from where they start. Okay, lastly, we have the gases will spread out and mix with each other without even being stirred. And this process is something we've probably learned about in other science classes, and that's what's called diffusion. Okay, and diffusion is the spontaneous mixing of particles of two substances caused by random motion. And if you think about, we've all experienced this, even though it's got this lovely definition, but this is why smells will essentially spread out in a given space. If you have a smell, a particle that has a particular smell to it, and it gets released, in one section of the room, those particles are on the move. They are trying to get as far away from each other as possible. So that's why the smell may hit, the people that are near it first, then it's going to hit the next people, and then maybe by the time it gets across the room, these people don't even smell it too bad, because those particles are so far apart that the concentration is that much less. Okay, so this is going to be diffusion, which again is our last physical properties of gases. Okay, I hope that helped.